All right, so that's what I want to explain is why is this the case? At least sketch out why is it the case that we have only simple fundamental interactions with such a tiny menu of states. And to begin with, we're going to go back to something very, very basic and talk about units. This is the bane of the existence of many high school physics students. Certainly, it was of mine. And part of the reason units are so annoying is that they're human constructs. So the first thing to do is to talk about natural units. In order to do that, we make use of the fact, going back to Max Planck, that we have constants like the speed of light and Planck's constant in quantum mechanics that let us convert distances to times via the speed of light and convert energies into times via Planck's constant. And in this way, we can reduce all units to one unit. We can make that unit, for example, a unit of mass or energy. So we say in choosing natural units that we put h bar and c to 1, but just so I give you an idea of what these units look like, the size of a proton is units of length. Length has units of 1 over, the length has the same units as time. Time has units as 1 over energy. So a length has units of 1 over energy. Okay? So the mass of the proton is what we'll use as our unit. It turns out to be very close to 1 giga electron volt. Okay, so if it was up to me, I would just define the giga electron volt to be the mass of the proton. But then in these units, the size of the proton, which is around 10 to the minus 14 centimeters, would be 1 over a giga electron volt. And now we could talk about more familiar things in these units. For example, my height. I'm around 10 to the 16th inverse GeV. And you see, that's a very useful way of characterizing my height. You could describe how tall I am to someone who lives in Mars, who's never been to Earth. Instead of saying I'm about 1.5 meters tall, which means that if you put me end to end next to this bar in Paris, the ratio of my length to the bar in Paris would be close to 1.5. They have never seen that bar in Paris. Instead, if you say that I'm 10 to the 16th inverse GeV tall, they'll know what that means, because it means that they stack 10 to the 16 protons on top of each other to get around my height. Similarly, my mass is 10 to the 29 GeV, and that's also useful. It tells you that I'm made out of around 10 to the 29 protons and neutrons. If you're lucky, the rest of this lecture time will be around 10 to the 27 inverse GeV. And an inverse GeV, because that's it's 10 to the 27 times how long it takes for light to traverse the distance of around the size of the proton, and so on. All right, so we only have this one unit, but now let's return to some very basic things that you probably all remember from high school physics. So if we look at the electric force between two electrons, we know that it goes like some charge squared divided by r squared. But now if we use what we just learned about the units, remember force has units of mass times acceleration, and that is units of 1 over length squared. Okay, so there's a 1 over length squared already here, so we learned something interesting, that this coefficient q squared is just a pure number, and that's around 1 over 137. That's its famous fine structure constant. On the other hand, if I look at the force between two electrons, it's g Newton times their masses over r squared. So that tells us that g Newton m squared is dimensionless, but g Newton itself has units of length squared. And in fact, that's what it is. G Newton in these natural units is 10 to the minus 33 centimeters squared. That's its famous Planck length squared. 10 to the minus 33 centimeters is a ludicrously tiny distance compared to any distances we've probed. As I've said, the tiniest distances we're probing at accelerators is around 10 to the minus 17 centimeters. So the tininess of this 10 to the minus 33 centimeters of this length scale associated with gravity of the Planck length relative to normal human length scales is a reflection of the extreme weakness of gravity compared to all the other interactions. And 1 over L Planck, yes.
Can I interrupt you? I'm not a physicist at all, so I might be asking a very stupid question. I got excited by the fact that you said this is school physics. So, you know, like the fact that you're talking about electric force here. Electric force, I mean, it's a force. So, I mean, school physics tells force has some unit, right? I mean, it's mass into acceleration, so it has to be some unit of mass into meter per second square or something.
Exactly. Exactly. Yes. Yes. Exactly. So that's just what I converted that for you is something in natural units. So as you say, it's mass times acceleration. So what is acceleration? Is velocity over time. Okay. So what are units of velocity? Velocity is dimensionless in these units. Okay. If I want to say that something is moving at 3 meters a second, what is that? There's a dimensionless number there, which is around 10 to the minus 8. Okay, because that's 10 to the minus 8 times the speed of light. Okay, so the velocity is dimensionless. So any velocity is just given by a dimensionless number. So acceleration has units of velocity over time, so that's 1 over time. Mass has units of energy, which is also 1 over time in these natural units, or 1 over length, because I can convert between time and length. So you see that force has the same units as 1 over length squared, okay, or the same units as mass squared. Okay, so that's what's beautiful about these natural units is you can convert every unit. You don't have to remember all the stupid units. You can convert every unit to this basic one. And then when you do that, you discover some interesting things that the electric force is actually associated with a fundamentally dimensionless parameter, 1 over 137. That's small. Whereas the gravitational force is not. The gravitational force is associated with this dimension full parameter, and therefore to say whether gravity is weak or strong. So you see, in an invariant sense, electromagnetism is weak because the strength of the interaction is a small number, around 10 to the minus 2, 1 over 137. But not true for gravity. Gravity is astonishingly weak when the distances are much larger than 10 to the minus 33 centimeters. But conversely becomes very strong when the distances become comparable to 10 to the minus 33 centimeters, or the energy becomes comparable to this Planck energy of 10 to the 19 GeV. The only reason we notice gravity, despite its extreme weakness, is it doesn't cancel out compared to all the other forces, of course, which do cancel out. But already if you take a pair of hydrogen atoms and hold them a millimeter apart from each other, the residual electric forces between them, known as the van der Waals force, is already stronger than gravity at around that scale. So that gives you an idea of how ridiculously weak gravity actually is. Okay, so did that answer your question?
Yes, I think that's the best way under the circumstances.
Okay, well, we can come back to it at the end of the talk. Okay, so, all right. Okay, so all right, so much about units. Now let me remind you of another aspect of that becomes obvious from these units. If we think about the basic process involving the collisions of particles, quantum mechanics tells us that we can't predict exactly what happens, exactly what comes out. We can only predict the probability, but the probability is given as the mod squared of a certain amplitude, of what's called the probability amplitude. And so if I talk about the scattering between 2 electrons, I learn from here, it's got to be, again, this sort of basic process at some leading order. And the amplitude goes like, again, this charge here and a charge there goes like q squared, this is around 1%. And so, again, in a fundamental sense, the amplitude for the scattering is small. But that's not true for the exchange of gravitons. If I have a scattering between electrons, there's a gravitational component to it. Now this amplitude goes like g Newton times the energy squared. And so it's tiny when the energies are very small compared to this Planck energy, 10 to the 19 GeV. But if I extrapolate this formula, when the energy becomes larger than 10 to the 19 GeV, it blows up. And so therefore, already from here, we know that something new has to happen when the energies are comparable to 10 to the 19 GeV, around this Planck energy, because it doesn't make sense for the amplitudes to get bigger than 1. Probabilities cannot be bigger than 1. Something new has to happen at or beneath this energy scale. All right, so with that introduction about units, we can now understand something about a very important notion of effective theory. So let's go back. If we look, for instance, at the basic interaction between electrons and photons and quarks and gluons, and all the other ones that I mentioned in the standard model except for gravity, all of these guys are associated with small dimensionless constants. There's some detailed differences. This guy is around 1 over 137. This guy, around the energy scales that we probe it, is around 1/10, but there's still relatively small dimensionless numbers. On the other hand, imagine we had some interaction that involved, let's say, more photons coming out. Now, remember, I told you that already the fact that we get an inverse square law, I mean, it does die off with distance. So that means that just exciting one photon out of the vacuum is costing you something. It's harder and harder to do it as you go to longer and longer distances. And therefore, exciting 2 photons, 3 photons out of the vacuum is going to be harder still. You'll have more and more powers of 1 over length as you pull the electrons apart, further and further apart from each other. And that tells us, by that very simple dimensional analysis, that the strength of any one of these interactions that involves spitting out more photons has to actually have a positive power of some length scale in it. Again, just by units. So all of these interactions, if I have more things coming out other than just 3, all of them have a strength that goes like some length scale to a positive power. And what that means is that as long as you go to distances that are long compared to that length scale, they will be irrelevant and tiny compared to the leading interactions you can have that are the very, very simplest ones. So that tells us that at low enough energies, only this basic ABC type interaction will be relevant. Okay, so that's the first thing. Sorry. Yes.
Yeah. Is that why you said that you cannot have something like with 12 particles interacting?
Exactly. This is the explanation for why we can have something with 12 particles interacting. In fact, it tells us more. It says that even if there was, in some sense, some fundamental 12 particle interaction, it would be irrelevant. You wouldn't notice it at long distances. What would dominate the world at long distances are the very simplest interactions. Okay.
Oh, thanks.
So that's the explanation for that point. Now let's talk about why there's such a tiny menu of spins. And first, we have this attitude that we're going to describe physics at very, very short distances first. That's the basic reductionist paradigm. And at very short distances, because of quantum mechanics, means very high energies. And so what we want to do is, if we're imagining particles smashing into each other at very high energies, clearly we should be able to ignore their mass in first approximation. I'll come back to this important point in a second. There's a footnote to this point, which is the entire story of the Higgs particle. But to begin with, we're going to just think about the particles as being basically massless. Now, when the particles are massless, there's something very important, that the spin that they have, we can only talk about their spin either in their direction of motion or opposite to the direction of motion. I'll come back and explain this point a little more later. So the spins that they have are, you can also call helicity, or from high school physics, maybe the polarization of electromagnetic radiation. Okay, so we can think of it as how they spin either in the direction of motion or opposite to the direction of motion. Okay. All right. So now let's come back and imagine that what you might think of as the simplest a collision between the simplest collision process, which is 2 particles in and 2 particles out. And let's think what we can say about this interaction on general grounds without knowing anything else. Well, this amplitude, whatever it is for the scattering process, can depend on the energies of the incoming particles and on the angle that the outgoing guys are going out in. So in principle, it depends on a lot of things. An energy and an angle, you could imagine writing down complicated functions of energies and angles. And in fact, the actual amplitudes of 2 in and 2 out do have some complicated dependence on energy and angle in general. But this is not the simplest scattering process you could imagine. The very simplest scattering process you could imagine is the one that we've talked about, where you have a particle coming in and splitting into 2 other particles. Now, here's the crucial point. If particles are massless, then this splitting, then by conservation of energy and momentum, the particles B and C that are going out have to be pointed in exactly the same direction as the particle A. All you can do is take the initial momentum and split it at some fraction going into B and going to C, but there's no angle. Okay, so there's nothing complicated. There's no complicated dependence on angle because there's no angles at all. Furthermore, it can't depend on the energy. And the reason why it can't depend on the energy is that by boosting to a different frame of reference, you can make the energy change. And yet special relativity will tell you that the amplitude should not depend on the reference frame.